Everybody, we have a finite series that we're trying to evaluate. Now, sometimes you don't need to explicitly write the terms out, but usually it's a good case in my opinion. I don't know if that's fair to say that, but anyway, notice that for the index of the summation is I, so for I equals 1, we get this term you see directly underneath it. For I equals 2, get a similar looking term, and it's consecutive odd integers in the square root symbols there. Now what would this be right here? This would be I is equal to 142. And we terminate this 143 term series with I equals 143. All right. Now, so what? What has that done for us? Well, let's go to the next line here. It turns out there's some nice algebraic approach to this, which makes life actually quite easy. Notice that each term is in this form 1 over the square root of an integer plus the square root of that integer plus 2, okay? Now, a very common algebraic trick is to multiply through by the conjugate. In this case, it's normally going to be a conjugate surd. And notice the form that we have right here, this piece right here is in the form x plus y. And I'm talking about just the denominator, okay? And then over here, we have x minus y. Now, of course, the object that is playing the role of y is the square root of a plus 2. Okay, now, when you expand this out, believe it or not, all that's left is minus 2, and it's not too hard to believe. This would just be x squared minus y squared, right? And again, I'm just talking about the denominators here. All right, again, if you square the square root of a, you just get a, and then when you subtract off, you would be left with only minus 2 as a survivor. Okay, now this gives us a way to transform each of the summands into something that's actually quite nice. Now, notice that, again, every one of the terms in this series are in this form, but each of these terms are in this form, okay? So we see the constant of negative 2 is present everywhere for all 143 of the terms, so we can just write it down one time, distributive property, okay? So we put minus 2 in the denominator, and you can see exactly what we have going on. This minus sign that you see right here, okay, is the minus sign all the way across. Okay, minus sign here, minus sign, all the way across, okay? So what happens here? Well, we get some nice cancellation. You guys recognize this is what they call a telescoping series. And you can't write everything down, but you sure get the picture of how things are going to cancel out. Okay, so these terms are going to cancel out pairwise. Everything on the interior is going to cancel out. And you're just going to be left with root 3 is surviving at the beginning here. Square root of 3, we'll leave it like that. Then the only term left is the square root of 289. Now that number was chosen intentionally. The square root of 289 is 17. 17 times 17 is 289. That's not hard to do, mental math. All right, so you have minus 2 right here. And so a cleaner way to write this would be root 289. I'll just write it out one more time here. Root 289 minus root 3 over 2. But we happen to know that 289 is a perfect square. 289 is equal to 17 times 17. All right, and so we actually get 17 minus root 3 divided by 2. 17 minus root 3 quantity divided by 2 is our answer. Okay, so let me get that circled. That's the answer. Now, we can take a look to see if this makes any sense. Square root of 3 is a number between 1 and 2, right? So this number would be, you know, somewhere around a, right? We'll just say circa lazy equal sign a, right? And that's probably pretty crude. Now let's go back to the beginning here. Notice that this particular sum right here would be the biggest sum in the entire series, right? And this is, you'll notice I'll put 1/4. Okay, approximately 1/4. It's got to be close to 1/4 because think of the square root of 4 being in both places, right? So you would have 2 plus 2 down here, and 1 over 2 plus 2 is 1/4. So both the square root of 5 and the square root of 3 are close to 2. So the square root of 1/4 has to be a reasonable, it has to be somewhere fairly close to 1/4, right? So notice, though, there's 143 sum ends. So you see what we would get right here, and this is a very crude upper bound, but you would get 143 over 4 is a very, very crude upper bound. And I say that because the very first term is the largest term, and it's only 1/4. These numbers get small really fast because the denominators get larger, the numerator remains constant, right? So we know that the sum, just as a sanity check, would be less than 143 over 4. Let's see, what's the closest number? 144 divided by 4 is 36, right? So this is right around 36. And again, I sound like a broken record here, but this is a very crude upper bound, and our answer is certainly well underneath. This doesn't inspire a lot of confidence, but this is the answer I got. I'm pretty sure it's correct. Python programmers could plug this in and just let the computer run through the iterations and get the solution. But anyway, that's the final answer, folks. We got a telescoping sequence due to this lemma that really minimizes the calculations. It takes each of these sum ends and converts it to something where you get this mass cancellation. And again, this is the final answer, 17 minus the square root of 3 over 2. Thanks for viewing.